Hey guys, and welcome to another physics video. And this video we're going to be having a look at Newtonian or classical mechanics. In the last few videos we went through the basics of vectors, and we're going to be using these vectors to start looking at some proper physics right now. And the first part of physics we're going to cover is classical mechanics. And it's basically the physics it's kind of the everyday familiar physics that we know around us. It describes things like balls falling or pulleys or levers or anything like that, anything sort of classical, down to earth. This is what classical physics describes. It doesn't take into account Einstein's general theory of relativity, and that basically, in summary, says that when things move very close to the speed of light, lots of funny things happen. We'll get more into that later on in this course, but for now we're just going to have a look at classical mechanics. But before we dive into the physics, there are just two bits of maths that I want to cover which will help us with our journey. So you've probably heard of some of this already, so I'm probably not going to talk for hours about it, but let's just review a couple of things. So firstly, let's consider what a derivative is. So any of you guys who've done basic calculus probably know the concept of a derivative. So say you have a function that says that, say y equals 3x squared. This is a function, y is a function of x. Then most of you guys can pretty much immediately see that the derivative of the function with respect to x is just 6x. And that is basically saying that the rate of change of y with respect to x is 6x. So basically, how do you take the derivative? Well, you simply multiply this by this and reduce this by 1. It's pretty much a pretty well-known thing. Now, one thing to note is taking the time derivative of any quantity. So let's say we have dx by dt. T in physics, of course, normally means time. If you take the time derivative, that you're finding the rate of change of that quantity. So in this case, we've got x being the position variable. Then if you take the rate of change of position with respect to time, then you'll get velocity, and velocity is the rate of change of position with respect to time. Now, of course, in vector form, we'd write this a little bit differently. We'd say that the rate of change of position vector with respect to time is velocity vector. So just the same thing, just I've substituted the x coordinate for the position vector r, and the same laws apply. You simply differentiate. Now, say we have v in its component forms, then you would just simply take the derivative of each component with respect to x. So fairly straightforward stuff right there. We can also call this quantity right here r with a little dot on top of it. Now this dot means time derivative. It means rate of change of this quantity. And sometimes you might see a double dot in front of it, which just means the second derivative. And one final thing to note is that if any position, if any quantity doesn't vary with time, so let's say that say we have a particle right here, it's staying still. So what does that mean? Well, that means its position r, its position vector, isn't changing. It's always the same distance from the origin. Then the time derivative is just 0. The velocity is 0. So the rate of change of any vector, if it's a constant, will just be 0. Now the second piece of maths that will help us is some very basic vector calculus. Vector calculus is quite a big topic, so we're not going to go through all of it, but we're just going to have a look at some basic vector calculus. And this is probably a little bit less familiar. I'm going to introduce the grad operator. Now let's start by saying let's say we have a function which we can call a. It's a scalar function, and it's a function of all three position variables. So it's a function of x, y, and z. Now, the gradient of this function, which we normally write with this little funny upside down triangle, this is the del operator. It's the actual symbol is called nabla, but the mathematically we call this del. We say that the del of a we can write as the derivative of this scalar right here in each direction. So basically we're taking the partial derivative. This is what this funny little curly d right here means. It means the partial derivative. And we're taking the partial derivative of a, but with respect to 3 different variables. So what we've got right here is the x derivative of a. We're treating the other 2 as constants, the other 2 variables as constants. Then we're taking the x derivative of a and then putting it in the x hat direction. So the result of taking the gradient of a is a vector. As you can see, we've got x hat, y hat, z hat components, whereas before we just started off with a scalar. We then take the 3 derivatives of the scalar and we kind of package them up as a vector. And what this does is it gives the rate and direction of change of the scalar. That's the physical interpretation of it. It gives the rate and direction of change of the vector. Grad A is a vector, and so the gradient operation turns a scalar into a vector. And as I said, it's essentially like making a packet of derivatives almost. And finally, the last piece of maths we'll need is how to take the integral of a vector. Now, like differentiation, you're probably fairly familiar with integration. So if you have a function which says that y equals 6x squared, then the integral, which we write like this, the integral of y with respect to x is simply, well, we add 1 to the power and then divide this number by the new power. So we're going to get 2x cubed. Well done, Paz. You've forgotten basic calculus. Nice one. Wow. Anyway, moving on. But of course you remember to add this plus c, or this constant of integration, after you do any integral. That's kind of basic calculus, and of course, you know, this plus c would just disappear when you differentiated it. So when you integrate, you have to add the plus c. But how do we integrate a vector exactly? Is that going to be much different to integrating a scalar? Well, not too different. It's kind of similar to how you would differentiate a vector. You would do it component by component. But let's say you have a vector that you want to integrate, and that's vector A. Now, normally when you're integrating a vector, the actual path in which you want to integrate the vector along is written as ds right here, the little ds. That's the path that you're integrating the vector along. And what you do, well, you basically just break this integral up into 3 different components. This path right here, any sort of path in space, has obviously an x component, a y component, and a z component. So you would simply integrate the x component with respect to x, and then add that to the integral of the y component with respect to y, and add that to the z component of this vector with respect to z. And that's essentially what the dot product does. It says, you know, go with the line that go along the part of the integral that is parallel to that component of the vector. So that's a useful little formula that we'll be using from time to time. And you'll be delighted to know that that is all the maths will be needed. So without further ado, let's get on to the physics. Now, classical mechanics is really fundamentally built upon 3 laws of motion that were developed by Isaac Newton, and you've probably heard of Newton's 3 laws of motion. The first law states that a body moves with constant velocity unless acted upon by a net force. So, what does that mean exactly? This is Newton's first law right here. So let's say we have a particle just sitting here at rest. what would you expect this particle to do? Well, it's not going to move, is it? It will just stay at rest unless there's something to cause it to move. It's pretty basic stuff, but a very important concept. So, if you've got a particle just sitting there at rest, then it ain't going to move unless it's being acted upon by a net force. Alternatively, if you've got a particle that is moving at a velocity v in that direction, so say it's moving that direction with a constant velocity, constant speed v, then it will continue to go at constant speed v unless acted upon by an external force. So the velocity will not change unless it is acted upon by an external force. Now, you might think this is a bit counterintuitive because, of course, when you have, say, a ball that's kind of rolling along a surface, then you're probably thinking, well, it's going to slow down. Well, the reason it slows down, of course, is that there is an external force that's acting. There's, a bit of air resistance, there's a bit of friction from the ground. And so those two forces, plus maybe a couple of other forces, are actually causing the ball to slow down, as there is a net force that is in the opposite direction of motion. So if the ball's going that way, then the friction and the air resistance will be trying to slow it down, and so that's why the ball will slow down. And Newton's second law actually follows on from this idea right here. So it basically says that if you do want to move something, or if you do want to change its velocity, then you have to apply a force. And we write this formally as the net force that's acting on an object, and of course force is a vector, is equal to the mass of the object multiplied by the acceleration of the object. And F net is the vector sum of all the forces acting on the body. So say you have a body which is being acted upon by multiple different forces. So say you've got this block right here. It's going to have a force that way. It's going to have a force that way. It's going to have maybe some force that's going off like that. You basically have to take the vector sum of all these forces that are acting. And of course, the vector sum is where you have to take into account the direction as well as the magnitude of all these forces. And then from that, you can work out the acceleration, and you'll work out the direction in which the force causes the mass to accelerate in. Now, we define momentum as P equals mv. And momentum is a vector, just like force, so is velocity. But for now, I'm just going to consider the magnitude of these quantities. They are technically vectors, but we're just going to consider the magnitude. So we can write the momentum as P equals mv, where these are all just now scalars. This is assuming it's all in one dimension, so we don't have to worry about vectors. Now, if we differentiate both sides with respect to time, then what are we going to get? Well, dp by dt is going to be equal to the derivative of this hand side with respect to time. Well, the mass isn't going to change. The mass is just going to remain constant. And you should know that when you differentiate, you do end up with a constant. Any constants don't carry forward. But differentiate velocity with respect to time, and you end up with dv by dt. But what's the rate of change of velocity with respect to time? Well, you should know that is just acceleration. So we get dp by dt is ma. But what's ma? Ma is just the force. And so we've shown that an alternative way of expressing Newton's second law is saying that force is the rate of change of momentum. And we can just simply formalize this by saying F equals P with a little dot on top of it. So force is the rate of change of momentum. And finally, with Newton's third law, that basically says that every action has an equal and opposite reaction. And so what does that mean exactly? Well, say we have a block that's kind of resting on a table right around here. Well, this block is going to exert a force on this table right here. And that force is, of course, due to gravity. You know, the block has a mass and therefore it has a force due to gravity. But why does that body not fall through the table? Because, of course, Newton's second law says that any object acted upon by a force will experience an acceleration. And there's no obvious sign of any other forces acting on this block. Well, in fact, there is another force. It's the normal reaction force that is exerted by the table on the block. And in this situation, it acts that way right there. So it's basically saying that if you have body 1 and body 2, then, and if they're in contact, then body 1 will exert an equal and opposite force on body 2 as body 2 exerts on body 1. They always have equal magnitude but opposite direction. Now, let's take a look at Newton's second law and have a look at it in a bit more detail. We know that force is a vector quantity and therefore it follows all of the rules of vector algebra. And as I said, if we have a number of forces acting on a particle, then we know that the total force is, of course, simply the vector sum of all the forces. And this concept right here is known as superposition. So let's have a look at an example of this. So let's say we have a particle right here, and it's subject to two forces in this case. So we have force 1, which is acting in that direction, and we'll call it F1, the little vector. And we have another force, force 2, which is acting in that direction right here. So we have a particle that is being acted upon by two forces. And the values of these forces, I'm going to tell you, F1 is 3 x hat newtons, and F2 is 6 x hat plus 2 y hat newtons. Now you can probably tell I haven't quite drawn it very well because it kind of looks like, you know, it's taller than it is wide, but it's not to scale. So, so the question is, what is the net force acting on this particle? Well, we know that the net force is the vector sum of all of these forces. So we know the net force is simply F1 plus F2. And of course, how do we add vectors together? Well, we simply add it component by component. So we add 3x hat, which is F1, to F2, which is 6x hat plus 2y hat. And that, of course, gives us 9x hat plus 2y hat newtons. And that is known as superposition. But supposing you wanted to try and find the magnitude and direction of this force. Well, that's fairly easy to do. We know how to do that. We know that the magnitude of the force is simply the square root of the x component and the y component. So we simply have the square root of 85, which you could, of course, evaluate on your calculator. And the direction in which this force acts with respect to the horizontal is, of course, just the arctangent of the y component over the x component. And that, of course, is, we should call that theta right there. And that, of course, is 12.5 degrees. So that gives us the magnitude and direction in which the net force acts. So we've got two forces right here. We can combine it as if there was an effective net force, just one effective force, but moving it in a particular direction. And its magnitude is 85, square root of 85 newtons, and it acts 12.5 degrees to the horizontal. And you'll encounter a lot of problems in which the very first thing you'll have to do is resolve the forces which are acting on a system. It's one of the first steps. You draw out your situation, you draw out all the forces that are acting on the particle, and you'll basically just end up with a set of equations in which you can solve for certain variables. So you might end up with a simultaneous equation, or you might be asked to come up with an expression, but you typically start by just resolving forces on particles. and then saying that the net force is equal to the mass times the acceleration from Newton's second law. Now, from these three laws of motion, we can actually start to derive some pretty useful equations. And as I said, all the classical physics just kind of stems from, Newton's laws, really. And these are some of the useful equations that we're going to start deriving. Now, we said earlier that acceleration A is simply the rate of change of velocity. So A equals dv by dt. For this section, I'm not going to bother too much considering about vectors. Normally, a lot of the time, you can just work in scalars and then think about the direction in which things are going in afterwards, because often the vectors will reduce down to the scalars by means of a dot product or something. Everything will happen in a certain direction. But vectors are just a very useful way of handling these quantities, like force, for example. But anyway, let's say we know that the acceleration is the rate of change of velocity with respect to time. Now, we can also write this as the change in velocity, with these little delta symbols right here. D basically represents an infinitesimally small change, but if the acceleration is constant, which is a key thing that we're going to be talking about here, we're going to be talking entirely about constant acceleration in this upcoming bit of the video. If the acceleration is constant, then we can actually change this into the change in velocity divided by the change in time. Now, let's say we have a particle that's initially moving with a speed of u. This is initially. And then it's acted upon by some force, and that will cause it to accelerate to a different speed, v. So this is the initial situation, and this is the final situation. And hence, this is the initial speed of the particle, and this is the final speed of the particle. Only the magnitude of the velocity is changing. It's not changing direction. We'll consider that what happens later on. So we know that from this equation here, we know that the change in velocity is simply v minus u. And that happens, let's say that happens in a time t. So that is, of course, the acceleration. Now, if we bring the t up to the top right here, if we multiply both sides by t, then we'll get that at is v minus u. And rearranging for v, we simply get that v equals u plus at. And that is our first equation of motion. It says that if a particle starts with initial velocity u and accelerates with acceleration a in time interval t, then its final speed will be v. And that is our first equation. Now what we're going to do is we're going to integrate this equation with respect to time. So how do we do this? Well, let's integrate both sides with respect to time. We can do this. This is perfectly valid by the laws of algebra. So if we integrate v with respect to time, then we have to integrate this side with respect to time. So what are we going to get when we integrate this? Well, we're going to get that the integral of velocity with respect to time is, of course, displacement. And displacement we represent with letter s. So we get s on this hand side. And what if we integrate this? Well, u is simply a constant, and we're simply going to get ut. And as for this term, we're going to get t squared, but of course we're going to have to divide by 2. So therefore we end up with a half a t squared. Now both sides of this integral are going to actually produce a constant because we didn't use any limits. So we're going to put a plus c right on the end there. But we can simply replace that constant of integration with something more physical. Now what we can say is that when time equals 0, the initial displacement is equal to 0 by definition. There is no displacement at time is 0 simply because it hasn't had any time to displace. So we know that when t equals 0, s equals 0. So what are we going to get when we substitute all this in? Well, we're just going to get that 0, which is s, is ut, well, t is 0, so that term goes, plus a half a t squared. Well, again, t is 0, so that whole term's going to go, plus c. So we can simply see that c is just equal to 0, as there's no displacement at time equals 0. So therefore we can simply rewrite this as s equals ut plus a half a t squared. And that right there is our second equation of motion. Now for our next equation of motion, what we're going to do is we're going to take this equation right here and we're going to square both sides. So let's start with this equation up here, v equals u plus at. Well, let's go ahead and square both sides of this equation. We're perfectly allowed to do that. So we get that v squared equals u plus at squared. And if we expand this bracket right here, we're going to get v equals u plus at, v equals u plus at. I've just done something about that squared. We're just going to make it a little bit easier to expand. Of course, you use the FOIL method of expanding, which you take, multiply these two, and these two right there. So what are we going to get? We're going to get u squared plus uat plus another uat, so plus a 2uat. This term in the middle, by the way, is kind of always known as the cross term. It's basically the term that involves both parts of the thing that you're trying to square. Because normally when you square something of this form, you're going to end up with that squared plus a mixed term in the middle. And this is the mixed term right here. And then you're going to get a squared t squared as our third term. Now what I'm going to do is I'm going to factorize the second two terms by taking out a factor of 2a. So we're going to get u squared plus 2a, and what are we going to get? We're going to get ut plus a t half a t squared. So taking out a factor of 2a, so if you multiply this out, then you're going to get 2uat plus a squared t squared, because that half is going to cancel with that too. But you'll notice ut plus a half at squared, what is that? Well, look down here, it's simply s. And so we can then just substitute in u squared plus 2as. So we get the v squared equals u squared plus 2as. And that is our third and final kinematic equation. And sometimes you might hear these equations called the Suvat equations. That's how I got to know them. And you can kind of see why. All of the variables are either s, u, v, a, or t. And these equations are very handy with working out any kind of motion problem, any kind of motion that involves constant acceleration. Unfortunately, they do only work with constant acceleration. And if acceleration isn't constant, then these equations will not hold. But for any kind of problem involving gravity, which is constant acceleration, then these are the equations to use. Now let's take this formula, v squared equals u squared plus 2as, and remember that the equation from before, Newton's second law, that a equals f over m. So we know that v squared equals u squared plus 2as. But a is, of course, f over m. So let's go ahead and substitute that into our equation. So we're going to get 2fs over m right around there. Now what we can do is we can actually multiply the whole thing by m and divide by 2. Might seem a bit of a weird thing to do, but you'll see why I'm doing it in a moment. So everything's going to get multiplied by m and divided by 2. So what are we going to get? Well, we're going to get half mv squared equals a half mu squared plus fs. Now, if you subtract a half mu squared from both sides, we're going to get that a half mv squared minus a half mu squared equals fs. Now you'll see that this term right here, this is the final kinetic energy of the particle, because of course you know that kinetic energy, K, is a half mv squared generally. So this is of course the final kinetic energy of the particle, and this is the initial kinetic energy of the particle. So let's substitute that in. So let's say that the K final minus K initial equals Fs. So we've shown that the change in kinetic energy, delta K, is equal to the force times the displacement. And that is what's called the work energy theorem. It says that the work done, which is the force multiplied by the distance, this quantity there is known as the work, is equal to the change in kinetic energy. So you've got a force, basically. This force is acting on a particle that has mass. The work done by this force is equal to the change in kinetic energy. Now, of course, the work is a scalar quantity, because of course energy simply has a value. It doesn't have a particular direction, it's just simply a number. So of course work, which is an energy term, is also a scalar. But of course force and displacement are vectors, and so therefore we can say that the work done is equal to the force dotted with the displacement. And of course if you expand that, then you're going to get it's going to be equal to the magnitude of the force multiplied by the magnitude of the displacement times the cosine of the angle between them. And a common example of this is, say you're trying to drag along this block along the floor right here, and you're applying the force. The force is of course, here's you. You're going to be trying to pull this block along the floor, but you're applying the force not in the direction in which the block is going to go, because this block is of course just going to slide across in horizontally. So any kind of vertical component of this force is just simply going to get wasted. And so therefore the only useful work is just Fs times this angle right here, because of course the displacement's going to be moving in this direction right here, so that's S, but the force is acting in this direction along here. And so any kind of vertical part is not going to get contributed to the work done. So the work done, the useful work done, is the force dot producted with the displacement. However, this is all assuming a constant force. Supposing the force actually varies along the path in which you're moving, in which the force is acting upon, then what can we say about the work? Well, we can actually break the path up into very, very, very tiny segments. And so here's our tiny little segments that we're going to take of the path. And we can therefore dot the force, which is of course changing with each part of this. And we call these little infinitesimal segments, we call them ds. So they're a tiny little segment of the path. And we can say that the total work done is equal to the integral from position 1 to position 2 of the force, which is now a function of the displacement, dotted with ds, the little vector element, of course. And if this is in one dimension, then it simply reduces to the work is 1 to 2 of f of x dx. That's of course in one dimension, but say you've got a force that's working in 2 or 3 dimensions, then that would be the vector formula that you have to use.